August 17, 1943, Northern France. 48 B-17 flying fortresses advanced toward the ball-bearing plants of Schweinfurt. The air temperature at cruising altitude measured -25 degrees Celsius. Wind velocity registered 60 knots from the west. Visibility extended to 10 miles under high cirrus clouds. From below, German radar operators at St. Paul detected the formation at 9:30 hours. A report was transmitted to Luftwaffe 3 Command in Paris. Intercept orders were issued to Jagdgeschwader 26, based at Lille and Abbeville. 24 Focke-Wulf FW-190A fighters were scrambled within 7 minutes. The American formation maintained altitude at 25,000 feet. Each aircraft flew in a staggered combat box of 12 bombers. Spacing between planes averaged 150 feet vertically and laterally. Each fortress carried 10 to 11.50 caliber Browning machine guns. Defensive arcs overlapped, producing continuous fire coverage in all directions. At 9:48 hours, the lead group crossed the Somme River. Luftwaffe ground observers reported, formation dense, layered, moving steady course east. Initial German comments described the pattern as clumsy and rigid. Radio intercepts later recorded the phrase Fliegend Wände, flying walls, uttered mockingly. However, subsequent engagements altered that perception permanently. The first interception occurred at 9:52 hours near Peronne. FW-190s attacked from the rear quarter at 15-degree elevation. Tracer fire from the fortresses met them before they closed to effective cannon range. One German pilot reported, "I saw a line of fire stretching across the sky." 3 FW-190s were hit in the first pass, 2 confirmed destroyed. Inside the American bombers, crews followed standard formation defense protocol. Top turret gunners called incoming bearings every 10 seconds. Tail and waist gunners fired in controlled bursts, maintaining ammunition discipline. Intercom chatter remained minimal, limited to verification of enemy direction and status. At 10:01 hours, the second German wave approached from 11 o'clock high. Messerschmitt Bf-109GS from JG2 joined the attack. Again, concentrated crossfire met them before they reached firing position. Gun camera footage later reviewed at 8th Air Force Intelligence confirmed the outcome. For enemy fighters destroyed, several damaged, formation integrity maintained. Observers on the ground near Cambrai recorded a continuous rolling thunder above. Spent cartridges fell in metallic rain from the bombers. Contrails twisted and intersected, forming broad white ribbons in the sky. No single bomber broke formation during the first 30 minutes of combat. The structural discipline of the combat box became visually evident to all witnesses. By 10:15 hours, the lead group neared the Meuse River. German controllers noted with frustration that frontal attacks were ineffective. A command message relayed, "Do not engage head-on." Losses unsustainable. The bombers continued eastward, maintaining cohesion despite sustained opposition. At 10:22 hours, one fortress from the low left element fell out due to engine failure. 3 Bf-109s pursued immediately. Within 20 seconds, 2 of them were destroyed by crossfire from the adjacent cells. The surviving German pilot broke off and climbed out of range. He later reported, "The Americans flew as one machine with 30 guns aimed at me." At 10:30 hours, the formation passed Charleville. Bombardiers began preliminary checks on the northern sites. Navigator reports confirmed course and wind drift. The crews maintained silence except for operational calls. the Luftwaffe command recorded an unexpected message: formation unbroken. Losses heavy. The combat box formation originated within the United States Army Air Forces in 1942. Its design followed months of analysis at the Air Proving Ground, Eglin Field, Florida. Engineers and tacticians examined losses from early daylight bombing trials over Europe. Reports from the 97th Bomb Group indicated that dispersed formations were too vulnerable. Single bombers were easily isolated by German fighters and destroyed within minutes. Colonel Curtis E. LeMay, commanding officer of the 305th Bomb Group, led field testing. His operational experiment sought to maximize mutual defensive coverage among aircraft. Using wooden models and flight trials, crews studied gun arcs and overlapping fire zones. A standard 12-plane box was established as the most efficient pattern. Each aircraft supported the next, forming 3 layers of vertical and lateral protection. Official doctrine named it the tight defensive formation. Air crews informally called it the combat box. Spacing and altitude offsets were mathematically calculated to optimize fields of fire. Each gunner's sector overlapped with adjacent aircraft by approximately 15 degrees. The pattern eliminated blind spots while preserving bombing accuracy. Training manuals distributed in mid-1943 emphasized precise formation discipline. Pilots were instructed to hold position regardless of incoming attacks. Deviation greater than 50 feet risked opening gaps exploitable by enemy fighters. Formation integrity was prioritized over evasive maneuvers. Every crew position had assigned fire responsibilities based on quadrant and altitude. The doctrine required extensive coordination. Radio silence during missions prevented confusion and interception by enemy direction finders. Crewmen relied on hand signals, visual cues, and predetermined timing. Formation leaders maintained strict altitude, speed, and course stability. Errors by one aircraft could compromise the defense of the entire group. German intelligence intercepted early reports about this new tactic in late 1942. Luftwaffe analysts dismissed the concept as impractical for sustained combat. Operational assessments predicted high vulnerability to concentrated frontal attacks. Early encounters over Saint-Nazaire and Lille seemed to confirm these assumptions. However, subsequent missions demonstrated rapidly improving American precision. By the summer of 1943, the 8th Air Force implemented formation doctrine across its bomber wings. Each wing comprised 3 groups, each with multiple combat boxes. The result was a vast, lead structure covering several miles of sky. Observers described it as an aerial fortress wall advancing at 150 miles per hour. For the first time, bombers could defend themselves without escort fighters. The concept also integrated with strategic bombing policy. General IRAC, ICA and Air Chief Marshal Sir Arthur Harris differed on doctrine. Harris favored night operations, ICA insisted on daylight precision bombing. The combat box made daylight missions feasible by increasing survival probability. It provided measurable data for assessing defensive efficiency and loss ratios. Statistics from August 1943 revealed the formation's effectiveness. Average losses per mission decreased from 18% to under 8%. Enemy fighter destruction claims increased by 40% compared to spring totals. Post-mission debriefings confirmed reduced crew fatigue and improved fire coordination. Intelligence officers concluded the formation had transitioned from experiment to standard procedure. By the time of the Schweinfurt Regensburg raids, the doctrine was fully institutionalized. Every crew underwent formation flight training at Basingbown, Kimbolton, and Thurley airfields. Engineers adjusted turret angles and ammunition storage to sustain prolonged defense. Aircraft maintenance crews inspected gun synchronization daily. Each element of the system reflected deliberate engineering and procedural refinement. When German pilots first encountered these formations, they underestimated the coordination involved. They viewed the dense geometry as cumbersome and easy to disrupt. However, gun camera footage and combat reports told a different story. The Luftwaffe soon recognized that approaching a combat box required extraordinary precision. Every misjudged angle meant exposure to multiple streams of converging .50 caliber fire. By September 1943, Luftwaffe Command ordered systematic evaluations of American formation tactics. At Rechlin Air Test Center, analysts reconstructed simulated attacks using captured BR-17 footage. Pilots of Jagdgeschwader 2 and Jagdgeschwader 26 participated in the controlled exercises. Each session measured approach angles, closure rates, and time under defensive fire. Findings indicated that traditional rear-quarter assaults were no longer sustainable. Statistical data confirmed the danger. An FW-190 approaching from 6 o'clock low had 3.4 seconds in effective firing range. During that time, it was exposed to at least 7 converging machine guns. Recorded hit probabilities exceeded 60% for defensive gunners. Damage rates made repeated attack passes nearly impossible without severe losses. German engineers proposed improved frontal tactics using high-speed dives. FW-190A6 and BF-109G-A6 models tested nose-mounted 20 mm 151 cannons for this purpose. The goal was to destroy bombers before entering their defensive perimeter. However, frontal engagements presented new difficulties. At combined closing speeds exceeding 600 miles per hour, aiming precision proved unreliable. Intelligence from Jagdgeschwader 11 described early results as inconclusive. Some bomber formations suffered fragmented losses, but overall cohesion persisted. Crews maintained formation integrity despite engine damage or structural hits. Even crippled aircraft continued to cover their sectors until fuel or hydraulics failed. Observers noted, they do not scatter. They move as one structure. At the same time, American commanders refined the combat box for deeper penetrations. New variants such as the staggered step-up and double-decker formations emerged. These allowed greater flexibility against climbing interceptors. Each successive box offset vertically by 50 feet, widening defensive overlap. This adjustment increased kill probability and maintained bombing precision. 8th Air Force operational analysis recorded significant data after each mission. Gun camera films were reviewed by intelligence officers within 24 hours. Enemy approach patterns were charted on transparent overlays for tactical evaluation. Adjustments were issued directly to group commanders before subsequent sorties. This feedback cycle accelerated learning and reduced recurring tactical weaknesses. Meanwhile, German fighter tactics evolved in response. Generals Adolf Galland and Werner Krapp ordered new operational trials using massed Sturmgruppen. Heavily armored FW-198 8GAR-2 variants carried 30 million Malawian Kwacha's 108 cannons for short-range attacks. These aircraft approached from the rear in tight wedge formations. They targeted bombers' weak tail sections, sacrificing speed for survivability. The first Sturmgruppen assault occurred on July 7, 1944. Against the 492nd Bomb Group. 30 FW-190s penetrated the outer defensive ring of B-24s nearest Chersleben. Within 3 minutes, 12 liberators were destroyed, but 20 German fighters were lost. American gunner reports confirmed the density of incoming fire as uninterrupted. Surviving German pilots described the experience as flying into a wall of flame. Further testing of formation attack geometry continued into 1944. At the Oberpfaffenhofen research facility, tactical models predicted 70% attrition in direct engagements. This forced Luftwaffe strategy to shift toward bomber interception at distant assembly points. Controllers guided fighters to attack before the bombers reached full formation. These early interceptions sought to exploit moments of organizational vulnerability. However, once the bombers established their combat boxes, interception success rates dropped sharply. Radar data from JAG Division 1 showed a 45% reduction in kill claims post-formation assembly. The Luftwaffe concluded that formation density had surpassed its offensive capacity. Analysts acknowledged that technical improvements alone could not counter structural defense. The problem had become one of geometry and discipline rather than firepower. In response, Luftwaffe staff recommended new bomber-destroyer projects such as the MIFA-10 and Do-335. These aircraft aimed to deliver heavier firepower from longer ranges. Yet none entered service in numbers sufficient to alter the balance. By late 1944, the combat box concept had achieved tactical maturity. German air defense units referred to it simply as the fortress formation. By late 1943, German command recognized the structural advantage of American formation doctrine. Luftwaffe combat evaluations classified the combat box as a tactical fortress. Reports to Oberkommando der Luftwaffe described it as aerial artillery with interlocking fields of fire. The tone shifted from mockery to analytical respect. Captive interrogations of downed U.S. crews confirmed the deliberate geometry of the system. At Wunstorf Airfield, technical officers compiled ballistic tables from recovered B-17 wreckage. Analysis revealed systematic gun coverage across every defensive vector. Each turret position was aligned to a known field sector, ensuring total arc integration. The findings established that no single approach remained statistically favorable. German analysts documented, every attack is exposed to overlapping machine gun fire. By December 1943, Jagdgeschwader leaders issued formal directives limiting frontal attacks. Only high-speed dives with altitude advantage were authorized. Rear and beam assaults were discouraged except under surprise conditions. Formation breaking tactics, once standard, were now labeled wasteful. Pilot attrition from sustained defensive fire exceeded replacement capacity. Intelligence Section 5 of the Luftwaffe recorded declining morale among fighter units. Reports cited continuous exposure to multi-angle gunfire and reduced engagement confidence. Average attack duration decreased from 6 seconds in 1942 to under 3 by 1944. Gun camera evaluations confirmed frequent premature disengagements. One pilot wrote, "We can only fire once before we are hit." American after-action records documented corresponding improvements in survival rates. Between March and August 1944, bomber loss ratios dropped below 5% per mission. Statistical reviews from the 8th Air Force Intelligence Division verified this trend. Bomber formations returning intact from deep Germany increased by 30%. The combat box had proven to be a functional shield, not a theoretical one. Post-strike photographic reconnaissance validated the precision benefit of formation stability. Bombing accuracy improved by maintaining uniform speed and spacing during attacks. Deviation among bomb site calibration fell within acceptable error margins. Crews that retained formation achieved higher target concentration rates. Formation cohesion directly correlated with both defensive survival and operational success. At the tactical level, gunners adapted to firing discipline protocols. Short bursts replaced continuous streams to prevent overheating and conserve ammunition. Inter-aircraft coordination evolved through pre-briefed engagement calls. Each gunner announced only bearings, elevation, and confirmation of impact. Operational brevity minimized confusion under attack. German aerial observers, once dismissive, began recording formation behavior for instructional purposes. Captured film footage was replayed at Luftwaffe training centers for analysis. One such reel, labeled Combat Box Defense, BE-17, circulated among new recruits in early 1944. The footage demonstrated converging tracer lines forming geometric grids around each bomber. Training officers emphasized the futility of direct assaults against such coverage. At the strategic level, the German Air Ministry acknowledged the formation's deterrent effect. Internal memoranda warned that bomber losses could not be sustained through conventional defense. Recommendations included greater emphasis on flak coordination and long-range interception. However, anti-aircraft batteries lacked mobility and response speed to match bomber routes. The result was a gradual erosion of aerial defensive capability. By the beginning of 1944, Luftwaffe interceptors increasingly focused on stragglers and isolated aircraft. The main body of formations was often allowed to proceed unchallenged. Field commanders noted that isolation occurred only through mechanical failure or fuel shortage. Even damaged aircraft often retained their position through disciplined throttle control. This collective endurance reinforced the perception of American aircrews as systematically trained and synchronized. At an operational conference held in Stuttgart in February 1944, findings were summarized. Colonel Hajo Hermann presented the assessment: their strength is formation, not speed or firepower alone. It marked the first formal German acknowledgement of formation tactics as a decisive innovation. From that point onward, Luftwaffe countermeasures focused on disruption rather than destruction. The shift signified a complete strategic realization of the formation's dominance. By early 1944, the combat box formation had reshaped Allied bombing strategy at the industrial level. 8th Air Force headquarters at High Wycombe issued new operational directives. All bomber groups were required to standardize assembly times and altitude blocks. These instructions ensured seamless integration of hundreds of aircraft into unified formations. The process demanded precise timing, fuel management, and navigation accuracy. Airfields across England were reorganized to support large-scale coordinated takeoffs. Ground controllers at Basingbourn, Thurley, and Kimbolton synchronized departures to the minute. Radar and radio beacons guided bombers into assembly patterns over the North Sea. The airspace between the English coast and the continent became a controlled corridor of movement. Formation assembly zones extended 70 miles in diameter at altitudes above 15,000 feet. Industrial planners within the United States adjusted aircraft production accordingly. Douglas, Boeing, and Vega facilities increased BA-17 output to 500 units per month. Each bomber underwent standardized turret calibration before shipment to European bases. Crew training cycles shortened from 6 months to 4, reflecting procedural efficiency. Formation discipline became a measurable skill evaluated before overseas deployment. Strategic policy makers linked formation tactics directly to long-range bombing feasibility. General Henry H. Arnold emphasized that mass formation defense allowed deeper penetration. Missions over Regensburg, Schweinfurt, and Berlin confirmed the operational endurance of cohesive groups. Survivability rates justified expansion of the daylight bombing campaign. Each mission generated new data for doctrinal refinement at the command level. British observers within Bomber Command noted contrasting approaches. RAF operations continued to rely on night dispersal tactics using electronic navigation. 8th Air Force daylight raids demonstrated measurable target destruction with reduced collateral spread. Joint analyses concluded that both methods complemented each other strategically. By late 1944, round-the-clock bombing became a consistent Allied objective. The combat box also influenced aerial industry design considerations. Engineers modified aircraft gun placements for optimized sector defense. B-24 Liberators received reinforced waist gun mounts to improve side coverage. The B-17G model introduced a chin turret for enhanced frontal firepower. Each adaptation responded to real data collected from combat box engagements. Aircrew logistics followed industrial precision. Ammunition loadouts were standardized across all bomb groups. Each .50 caliber gun received 500 rounds for mission duration. Maintenance personnel replaced barrels and belts according to pre-flight inspection protocols. The system operated as an integrated machine of production, procedure, and execution. German intelligence assessments recognized the industrial depth behind the tactic. Captured documents revealed the Americans' reliance on assembly line coordination. The Luftwaffe reported, "They fight as factories fly." Interrogated pilots confirmed identical procedures across separate bomber units. Such uniformity made disruption through deception or timing errors nearly impossible. At the strategic planning level, U.S. analysts calculated the ratio between formation density and survivability. Mathematical models indicated that doubling the number of overlapping boxes halved expected losses. This statistical validation justified increasing mission sizes from 300 to over 1,000 bombers. By mid-1944, formations extended for miles, forming continuous defensive corridors. Observers described the sky over Europe as filled with metallic grids in motion. Industrial production supported this escalation without degradation in effectiveness. Training manuals, airframe design, and gunnery doctrine shared standardized parameters. Each aircrew operated under identical checklists regardless of base or group. This uniformity produced operational predictability and reduced coordination errors. The formation became not only a tactical tool but a symbol of systemic organization. Within Germany, this development forced realignment of air defense resources. Flak divisions repositioned to concentrate near industrial corridors rather than isolated cities. However, dispersed bombing routes diluted their effect. The combat box could absorb limited flak damage while maintaining cohesion. This resilience frustrated German command structures dependent on concentrated interception points. By late 1944, Allied intelligence considered the formation an industrial weapon in itself. It represented the merging of manufacturing precision, logistical discipline, and tactical control. Air warfare analysts from both sides identified it as the first truly systemic aerial doctrine. It reduced reliance on individual skill and replaced it with procedural dominance. The result was a self-sustaining architecture of defense and offense combined. After the war's conclusion in 1945, Allied and German technical committees conducted detailed evaluations. Captured Luftwaffe archives contained extensive reports on the combat box phenomenon. These documents were reviewed by United States Strategic Bombing Survey investigators. Data confirmed that defensive formations had reduced bomber losses by nearly two-thirds from 1943 levels. The tactical innovation was classified as one of the decisive factors in the air war over Europe. At Wright Field, Ohio, returning aircraft were examined for ballistic and structural endurance. Analysis revealed consistent damage distribution across standardized defensive sectors. Turret mounts and ammunition feeds performed reliably despite heavy engagement cycles. Gun synchronization remained within acceptable tolerances across repeated missions. The findings validated the mechanical integrity of the combat box concept. American postwar reports categorized the system as a coordinated application of geometry and fire discipline. Crew's interview described the experience as procedural rather than heroic. Each man relied on regulation, not improvisation. Survival depended upon collective adherence to the manual, not individual maneuver. The standardized design of the formation had produced measurable and repeatable outcomes. German postwar officers provided similar conclusions during interrogation. Former JAG-WWII 26 pilot Franz Stigler described formation encounters as mathematical. He stated, "There was no room for courage. Only angles and velocity determined survival." Another report from Luftwaffe Group Command North characterized the boxes as aerial strongpoints. The terminology reflected an acknowledgement of structural, not emotional, superiority. The United States Army Air Forces converted these findings into institutional doctrine. Postwar bomber manuals emphasized group tactics as the foundation of aerial strategy. The principle extended to jet-era aircraft such as the B-47 Stratojet and B-52 Stratofortress. Formation integrity remained essential for both navigation and defense in coordinated missions. The legacy of the combat box persisted as a cornerstone of strategic air power organization. Academic studies during the 1950s further quantified its efficiency. Operational research divisions analyzed engagement films frame by frame. Each tracer trajectory was mapped to confirm gunner accuracy and formation geometry. The compiled data influenced future fire control computer development. Ballistic computation software for automated turrets derived directly from these wartime analyses. In parallel, NATO doctrine absorbed lessons from American formation strategy. Joint exercises conducted in 1952 under Operation Mainbrace replicated historical combat box parameters. Multinational bomber groups practiced unified spacing, communication, and defensive procedures. These operations confirmed that formation geometry remained relevant under new weapon systems. Radar-directed coordination replaced visual cues, but the organizational principle was identical. Former Luftwaffe analysts employed by post-war Western agencies contributed to comparative studies. They verified that formation tactics neutralized numerical inferiority by maximizing mutual defense. Reports concluded that technical mastery of discipline could outweigh superiority in individual aircraft. This assessment formed the basis for later air combat coordination models. The combat box was cited as the first evidence of air power behaving as a networked system. By the late 20th century, surviving veterans from both sides reflected in measured tones. Few regarded the concept as glamorous or dramatic. Most described it as mechanical necessity under industrial warfare conditions. Their accounts matched the archival evidence precisely. The combat box remained an enduring example of how organization redefined survivability. A 1946 U.S. Strategic Bombing Survey summary stated the conclusion clearly. Success derived from integration, not invention. Formation flying transformed aircraft into a collective weapon. This phrase summarized the doctrine's historical significance. It was the application of mathematics, not emotion, that determined dominance in the European air war. The geometry of defense had reshaped the future of aerial combat permanently. Between 1946 and 1950, systematic post-war studies documented the technical lineage of the combat box. At the U.S. Air Materiel Command, engineers dissected operational flight records from the 8th Air Force. Over 12,000 formation diagrams, gunnery logs, and mission reports were archived and cross-referenced. Statistical analysts from the RAND Corporation conducted mathematical modeling of formation efficiency. Their calculations confirmed that overlapping defensive arcs reduced exposure by 72% on average. Testing continued at Muroc Army Airfield using B-29 Superfortress aircraft. Crews replicated wartime formations at altitudes above 25,000 feet. Observers measured radar visibility, contrail interference, and dispersion under varying atmospheric conditions. The findings confirmed that structural spacing remained critical even in high-altitude jet environments. Optimal spacing of 150 to 200 feet persisted as the universal benchmark for formation stability. Engineers identified key hardware advancements derived from wartime experience. Gyroscope-stabilized turrets, electric ammunition feeds, and synchronized gun sights became standard post-war features. Designers at Boeing and Convair adapted these lessons into jet bomber architecture. The B-47 Stratojet employed tail radar fire control modeled after coordinated gun sectors. The later B-52 retained multiple defensive gun zones reflecting the same geometric doctrine. Training reforms followed similar principles. Air University at Maxwell Field incorporated formation systems theory into its 1948 syllabus. Cadets studied mathematical modeling of three-dimensional airspace defense. Lessons emphasized procedural discipline over individual maneuvering instinct. Command instructors repeatedly cited the wartime combat box as the foundational case study. International collaboration reinforced these doctrines. British, Canadian, and French officers participated in U.S. Air Force exchange programs. Joint seminars reviewed 8th Air Force data films frame by frame. The archival imagery served as a universal instructional standard. The emphasis remained on geometry, coordination, and measured reaction under pressure. German post-war engineers integrated similar principles into early Bundesluftwaffe flight schools. Advisors from the United States Air Force assisted in curriculum development. Simulation devices reproduced formation layouts using scale models and projected lighting. Exercises focused on maintaining consistent altitude, distance, and reaction timing. The training objective mirrored wartime lessons, discipline as a form of defense. Technological advancement transformed the concept without erasing its essence. Early warning radar and ground-controlled interception replaced visual alignment for coordination. Formation logic extended into digital command systems for synchronized bomber operations. By the early 1950s, automatic flight control computers began maintaining precise spacing automatically. This evolution confirmed the enduring utility of collective flight geometry. Theoretical documentation expanded beyond military application. Aviation research journals discussed the formation model as an example of distributed stability. Engineers identified parallels between bomber formations and industrial process control. The concept illustrated how feedback systems could maintain order under external stress. The combat box had become a case study in applied systems engineering. Within the United States, institutional memory preserved its operational vocabulary. Terms such as element, lead ship, and wing station persisted into the jet era. Even with the disappearance of manual gun stations, positional discipline remained essential. Airborne refueling formations, aerial mapping flights, and reconnaissance squadrons reused the same logic. The doctrine had transcended its wartime origins and entered standard aerospace practice. Post-war analysis concluded with one definitive observation. The combat box represented the first instance of group automation achieved through human precision. Before electronic computers, air crews functioned as synchronized mechanical components. Their consistency across thousands of missions formed an analog prototype of modern automation. In effect, the 1943 bomber formations operated as the earliest human-engineered aerial networks. The legacy of that structure continued to influence formation science into the Cold War. When Strategic Air Command developed nuclear alert protocols, it drew directly from these principles. Commanders specified group spacing, radio silence, and timing windows identical to wartime models. Operational diagrams in SAC manuals from 1951 resembled the 1943 combat box schematics exactly. The geometry of survival had become the geometry of deterrence. By the early 1950s, the combat box had evolved from wartime necessity to Cold War doctrine. Strategic Air Command (SAC), under General Curtis E. LeMay, formalized its structural principles. Formation integrity became the foundation of nuclear deterrent readiness. SAC training manuals outlined spacing, altitude tiers, and communication silence identical to wartime precedent. Aircraft now carried atomic payloads, but their flight discipline traced directly to 1943. B-47 Stratojet wings practiced mass takeoffs at intervals of 15 seconds per aircraft. These sequences created airborne formations spanning several hundred miles. Though jet propulsion had replaced propellers, the same mathematical order prevailed. Navigation officers used radar bearings to maintain electronic combat boxes invisible to the eye. This adaptation preserved coordination under the new requirements of jet speed and altitude. Formation logic expanded into radar and early warning networks. Command analysts identified the bomber formation as an operational model for distributed control. Each aircraft functioned as a node within a defensive grid, maintaining mutual awareness through signal timing. This organizational concept directly influenced development of airborne command and control systems. Later designs, such as the EC-135 and AWACS platforms, derived from this coordinated geometry. Technical reports from the Air Research and Development Command, ARDC, confirmed the transition. Formation algorithms inspired early flight automation projects during Project Compass and Project Linus. Engineers replicated bomber spacing behavior using analog computing systems. The experiments demonstrated that formation dynamics could be stabilized through constant data feedback. This insight became fundamental to modern autopilot and swarm flight technology. At the doctrinal level, formation discipline transformed from defensive necessity to strategic symbol. Massed bombers represented visible evidence of national readiness and organizational precision. SAC parades and air power demonstrations replicated the compact order of wartime formations. Observers interpreted them as visual manifestations of deterrent capability. The geometry once designed for protection now embodied political stability through control. Allied air forces incorporated parallel doctrines during NATO integration. British V-bomber squadrons practiced group flight configurations modeled on American data. Canadian and French strategic units adopted similar training procedures. Joint exercises in 1956 and 1958 measured internation synchronization accuracy. Deviation tolerances remained within 10 feet, matching wartime performance under analog conditions. Soviet intelligence documented these exercises through radar and photographic observation. Reports from the main intelligence directorate described the formations as a geometrically disciplined. Eastern analysts concluded that Western bomber organization compensated for numerical disparities. They referred to the tactic as collective precision warfare. The description aligned almost exactly with 1944 Luftwaffe terminology. The same geometric principle extended into tactical air operations. Jet fighters employed loose but structured elements based on bomber defense concepts. Two-ship and four-ship formations reflected adapted versions of mutual coverage arcs. Although combat speeds exceeded human reaction limits, coordination logic persisted. The lineage of the combat box thus influenced both strategic and tactical flight models. During the 1960s, computer simulation replaced manual plotting in formation studies. RAND analysts digitized 8th Air Force records to test network resilience under attrition. Results demonstrated that formation survival rates correlated strongly with communication redundancy. This verification reinforced the enduring utility of group coherence over individual maneuver. Even in digital simulations, the 1943 logic produced optimal survivability outcomes. Aerospace historians later identified the combat box as the progenitor of modern networked warfare. The principle of distributed yet interdependent defense became a template for electronic command systems. Each bomber in formation had functioned as both shield and signal relay within the group. Modern analysts recognized this as an analog precursor to digital combat networking. The tactical geometry of the 1940s had evolved into the architecture of information control. By the close of the 20th century, air-power doctrine still carried remnants of this heritage. Refueling trains, surveillance grids, and stealth strike packages maintained formation-derived sequencing. Even autonomous drones in early 21st century research referenced combat box spacing logic. Historians classified the doctrine as the first organized human-machine interface in combat aviation. Its endurance confirmed the engineering foundation beneath its wartime conception. In every period of application, the same rule remained constant. Formation coherence converted individual vulnerability into collective strength. That principle, first observed above France in 1943, became the lasting framework of aerial warfare. The geometry of order, conceived amid attrition, persisted into the age of computation. Its lineage traced unbroken from the propeller-driven B-17 to the algorithmic precision of modern flight. From 1943 onward, quantitative analysis became the foundation of aerial formation doctrine. Postwar statisticians compared the combat box to subsequent flight systems across multiple eras. Data from over 2,000 U.S. Army Air Forces missions were contrasted with jet-era exercises. The objective was to determine whether formation geometry or technology contributed more to survivability. The results showed that geometry and discipline remained the dominant variables. Records from the 8th Air Force demonstrated consistent defensive efficiency. Each 12-plane combat box maintained overlapping fields of fire within a 30-degree cone. Gunfire coverage exceeded 90% of potential enemy approach vectors. Later SAC simulations using jet bombers replicated identical protection ratios under electronic coordination. Mathematical modeling confirmed that formation logic remained scalable across generations. Analysts from the RAND Corporation published comparative studies beginning in 1948. One landmark report, Statistical Correlations in Aerial Defense Structures, outlined core findings. It identified group density, spacing, and communication delay as primary determinants of loss probability. The data indicated that a 15% increase in spacing reduced mutual support effectiveness by 40%. Conversely, compression beyond 100 feet caused turbulence interference and fuel inefficiency. British Air Ministry researchers conducted parallel assessments on V-bomber formations. Operational tests over the North Sea in 1953 verified optimal performance at staggered 200-foot intervals. Radar cross-section studies demonstrated that structured formations appeared as unified signatures. This property complicated enemy tracking but also provided mutual radar masking. Thus, the geometric foundation of the combat box continued to yield measurable advantages. In Soviet research archives declassified after 1991, similar evaluations were documented. Analysts at the Gromov Flight Research Institute reproduced formation spacing using Tu-16 and Tu-95 bombers. Their conclusions mirrored Western findings. Cohesion minimized interception exposure. The studies described formation stability as a collective survivability coefficient. This confirmed that geometry functioned as a universal constant in aerial warfare. A 1957 United States Air Force Operations Research Memorandum refined these conclusions. It expressed formation resilience as a function of unit count and angular coverage. The equation demonstrated diminishing returns beyond 36 aircraft due to coordination limits. These findings guided the design of SAC's cell system, a modular formation structure. Each cell mirrored the wartime combat box in scale and composition, optimized for modern range. International collaboration further validated the model. Joint NATO exercises such as Sky Shield II in 1960 employed comparative radar tracking. Observers noted identical stability factors between propeller-era and jet-era configurations. Loss simulations confirmed that failure to maintain position increased cumulative exposure exponentially. This established that formation precision remained the primary determinant of group integrity. The quantitative legacy extended into civil and scientific aviation. NASA's Dryden Flight Research Center conducted formation flight tests during the 1990s. The Project Autonomous Formation Flight referenced B-17 spacing models for aerodynamic efficiency. Fuel savings of up to 15% were achieved by replicating wartime geometry under computer control. This civilian application reaffirmed the enduring validity of historical tactical data. Academic institutions cataloged and standardized this information. The Massachusetts Institute of Technology's Aeronautics Department maintained digitized copies of wartime diagrams. Students analyzed bomber formation mathematics to study stability under perturbation. The research identified parallels with biological and robotic swarming systems. Thus, the combat box evolved from historical artifact to active reference model in systems science. Comparative assessment also influenced strategic planning methodologies. The U.S. Air Force incorporated quantitative modeling from the 1940s into digital simulation frameworks. Each mission planner used probability charts derived from formation defense equations. Modern air operations centers embedded these calculations into software algorithms. Through direct lineage, the mathematical logic of the combat box persisted in contemporary digital doctrine. By the 1970s, cross-national comparisons had confirmed a universal conclusion. Regardless of aircraft type, propulsion, or weapon system, collective geometry dictated survivability. The combat box remained the first verified empirical proof of that principle. Its data defined not only how bombers flew but how all aerial systems would later coordinate. In military terminology, it marked the origin point of networked operational science. By the end of the 20th century, military historians and aerospace analysts had completed the full evaluation cycle. 50 years of comparative data confirmed the combat box as the prototype of modern formation warfare. It represented the first empirical demonstration of system-wide survivability through coordination. From World War II to the jet age, its geometry proved universally scalable and repeatable. The principle of overlapping defense remained consistent across all major air power doctrines. In 1993, the United States Air Force Historical Research Agency published a complete review. The study, Formation Tactics in Strategic Bombing, 1942 to 1989, summarized every known dataset. It concluded that group flight discipline generated more measurable survival benefit than armor or speed. The report described the combat box as the mathematical foundation of coordinated aerial warfare. This assessment established its enduring relevance beyond its original tactical context. Digital reconstruction projects in the 2000s further verified its precision. Air combat simulators recreated wartime formations using high-resolution positional telemetry. Each simulated aircraft reproduced 1943 spacing, altitude tiers, and gunnery coverage angles. Data from these trials matched original mission film measurements within a 3% margin of error. Such accuracy confirmed that wartime records were not estimates but engineered procedures. NATO training syllabi retained direct references to American formation discipline. Air-to-air refueling, reconnaissance coordination, and early warning network drills used modified versions. The organizational logic persisted: maintain fixed spacing, overlapping fields, and controlled communication. Modern jet tankers and strike packages operated as digital successors to the same geometry. The continuity between eras remained exact in structure if not in speed or scale. By contrast, post-war German analysts incorporated their wartime observations into academic instruction. Bundeswehr Air University courses addressed formation theory and operational geometry. Students reviewed archival diagrams from 8th Air Force reports. The curriculum emphasized that combat box cohesion represented the ultimate countermeasure to attrition. It demonstrated how organized precision could neutralize qualitative inferiority in individual aircraft. Civil research institutions also adopted the concept as a model for cooperative systems. Aerospace engineers studied the combat box when designing satellite constellations and drone fleets. Formation logic guided calculations for orbital spacing and mutual data relay coverage. The principle of overlapping zones ensured redundancy and minimized single-point failure. Thus, a World War II tactic became a framework for autonomous coordination in the 21st century. Preservation efforts secured its legacy for archival and educational purposes. At the National Museum of the United States Air Force, Dayton, a permanent exhibit opened in 2010. The display included formation schematics, Norden bomb site mock-ups, and declassified mission maps. Interactive screens allowed visitors to observe real-time reconstructions of B-17 combat boxes. The presentation described them simply: mathematics in flight form. Analytical literature emphasized the impersonal nature of its success. No single inventor or commander claimed authorship. The formation evolved collectively through thousands of operational refinements. Its endurance across decades reflected institutional adaptation rather than individual genius. This anonymity underscored its character as a systemic innovation, not a heroic one. Military institutions worldwide continued to teach its geometric discipline. Chinese and Russian flight academies included comparative lessons on World War II formation logic. Translated technical manuals detailed altitude differentials, lateral offsets, and gun convergence patterns. Even with new weapon technologies, the logic of mutual coverage remained instructive. The geometry of the combat box had become universal military literacy. In 2023, a joint NATO symposium on cooperative flight networks cited the formation once again. Delegates noted that every connected aircraft in a digital battlespace functions as part of a modern combat box. This phrasing formally extended the term into the era of automation and artificial intelligence. The principle of coordination, first defined above France in 1943, remained operational 80 years later. Its endurance symbolized the transition from analog warfare to network defense systems. The final conclusion of all comparative and technical studies was identical. The combat box represented the moment when air power became mathematics. Its geometry replaced instinct with calculation, and individual motion with structured survival. The doctrine's lineage extended from piston engines to data networks without conceptual deviation. Immeasurable, Factual terms, it remained the most influential aerial formation ever devised.